should I get started? I think now you guys are on mute.
Can you hear me now?
Yeah.
Okay.
Yeah.
Okay. So, Professor, if you want, we can start right now.
Yep. Perfect. Yeah, thank you so much. Hi, everyone, and welcome to the second session of the day. My name is Cynthia Rosque. I'm really excited to introduce the Services and Business Application and Industry and Short Papers session. Today, we're going to learn about safety and operational implications of autonomous construction sites. Then we're also going to touch a little bit on digitalization from the oil and gas sector, and also the state of the practice of BIM in the United States. We're also going to talk about BIM-based process control. And then finally, we're gonna hear from information communication needs of an autonomous excavations. So to get us started, our first presentation is titled Taxonomy for a Connected Autonomous Plant by Brown, Walker, Emily. I see they are sharing screen.
Hello, can you hear me?
Yeah.
Can you see me? Excellent. Do you want me to get started? Cool. So, hello everyone, my name is Ross. I'm pleased to join you today to present our paper, A Taxonomy for Connected Autonomous Plant. This work was commissioned by National Highways, who look after the strategic road network in the UK, which is 4,300 miles of motorways and major roads here in the UK. Investing £4.5 billion in 2020-21, they're alongside HS2, who's one of the largest construction clients in the UK. So they operate, maintain and improve the network. And as part of this, they're kind of heavily involved in the construction phase of their operations and the road projects that they build. So their involvement in the construction phase has led them to be really interested in identifying ways which they can improve safety and efficiency on their projects and automate.
I'm sorry, I think that Mr. Ross Walker get no internet. Can you hear me?
Sorry, I think you lost me there for a second, did you? Yeah, I'll carry on, shall I? 1 second, share my screen again.
Okay, thank you.
Okay, sorry about that. Don't know what happened there. Yeah, so this roadmap was launched in 2020 and sets out the plan for how to reach this 2035 goal. And we're looking at holistically what's required to basically achieve this goal of autonomous machines on site. So the next slide. So the levels taxonomy highlighted here as one of the first tasks, and it stipulated that having a unified language to describe the capabilities of autonomous construction machines, we can accelerate the speed at which developments in this field are made. So to that end, National Highways are in quite a unique position because they're able to mandate the use of such a taxonomy across their £4.5 billion expenditure. So this is a key reason why working with a client organization for a project like this makes a lot of sense. So specifically, the objectives of the taxonomy, beyond just a general ability to communicate about capability, are to support and catalyze developments of technology roadmaps amongst plant and technology manufacturers, to enable procurement processes that incentivize the development of CAP within construction and the rest of the supply chain, and to support innovation practices by providing an understanding of the safety and operational implications of deploying automation on construction sites. So the methodology that we chose can be summarized as review, adapt, and validate. So we first looked at other industries where automation is perhaps more advanced commercially, and looked at the taxonomies that they use. We adapted them to suit the construction use case, and we then validated our taxonomy with stakeholders from a range of plant machinery organizations, so JCB, Caterpillar, Leica, these kind of manufacturers. These stakeholders were essentially brought together at the start of the project to assist throughout the CAP project with validation exercises like this. So the concept of developing levels of automation has been applied in a wide range of industries, including on-road vehicles, aviation, metro, and manufacturing. The taxonomies developed in each of these industries have employed different methodologies and produced different classifications based on the particular needs and the requirements of that industry. So we carried out a systematic review of the existing taxonomies to identify the practices and aspects of the other taxonomies that are most useful to the development of the classification of automatic capability for plant and construction. And the figure here shows the search terms that we used. So the first key piece of literature goes back to 1978, with Sheridan and Verplank looking at subsea teleoperation. And this provided a good baseline to understand the flow of different states between full human control to full machine control, and then the steps in between. This was then extended in a seminal work by the same author in 2000, where they divided the information processing steps into 4 classes and noted that the previous 0 to 10 scale applied to only one of the 4 classes, so decision and action selection. And the 4 classes were information acquisition, information analysis, decision and action selection, and then action implementation. These are shown here in this figure. What's noteworthy is a kind of lack of any classification beyond just high and low levels of automation. So that's something to bear in mind as we go later on. So we then reviewed the taxonomy that exists already in different industries. So again, the general approach identified across different industries is that human participation is required where there is a low level of automation. As the level of automation increases, this advances to only requiring human intervention. And then when there's no need for a human involvement at any point, then clearly we have full automation. And when considering the development of the levels, they were kind of broadly based on information acquisition and processing, decisions on actions to be made, and then carrying out the decided actions. So this table shows that information processing is broadly split into the same categories across each of the reviewed taxonomies. Although the automotive taxonomy combines acquisition, analysis, and selection into one task. This creates a simpler taxonomy, but hides some of the detail and includes the possibility of human-machine cooperation. And the simpler taxonomy for automotive is similar to those that have been developed in agriculture, mining, and metro, where the levels of automation are defined on the basis of where a human has to intervene. So again, it's that kind of intervening versus full control versus full human control. So in contrast to that, the aviation and military UAV industries developed a more comprehensive taxonomy, which considers the automation of each aspect of the information processing stage to create a 4-dimensional taxonomy. And this increased level of detail is useful because construction is more complex than some of the other industries and features numerous different aspects which can all be automated to varying levels. So it's proposed that the CAP levels of automation will be based on this 4-stage information processing employed by some of the previous taxonomies that we've shown here. And these classify the capability of machines in a way that is comparable to how humans actually carry out information processing. So this figure here shows the stages of information processing that we define in this project. And you can see how they kind of flow together. Responsibility and fallback is an additional stage which refers to who or what is responsible for controlling the automated system. Should it, for example, leave its operational design domain or subsystem of the machine fails and have to fall back or onto a different system or fall back to human control. So this graphic describes each stage of the taxonomy that we've created. We don't have time to go into detail of all of them. We'll go into one of them in a minute, but observe broadly describes how automated system is at acquiring data from its environment. Understand describes how automated the system is at processing data to determine its environment based on its observations. And then decide describes how automated the system is at deciding what action to take based on its environment. And then act is how automated the system is at carrying out an action based on a decision. And then responsibility again describes who or what is ultimately responsible for the continued safe operation of the machine. So to give one example, consider the understand stage. To accommodate different aspects of the understand stage, we consider three subcomponents. So compare, predict, and learn. And these are defined as compare, which is understanding the current state by comparing the observations to existing values and thresholds. Predict, which is understanding the future state through a predefined model against which the observations are applied. And then learn, which is understanding the future state by learning from the outcomes of past decisions and actions and then applying this in that stage. And then, although we've not included it in this paper, there's also in our final report about this, there's additional guidance at each level of examples and how to apply each level at each stage. So we released the taxonomy to our stakeholder group and then conducted a series of workshops to introduce the levels. And then following this, conducted a survey to understand how our stakeholders thought of the utility and the ease of understanding of the taxonomy, both on a scale of 1 to 5. The utility score was 3.9 out of 5, and the ease of understanding score was 4 out of 5, both with reasonable standard deviations. And then we also provided sufficient information for manufacturers to conduct their own self-assessments against some of their own machines. And this was conducted by Caterpillar, Bomag, and Built Robotics in the US. So the self-assessment was in agreement with the team's assessment, which kind of reinforced the ease of use of the taxonomy. And the examples are shown in the figures here. So we think we're onto something with this, and there's still plenty of work to do on it before it's widely used for sure, but we're keen to get feedback from people, this community, academia more widely, but we're also applying these in the real world on more sites, so a number of national highway sites. We're also involved in a PASS 1892 and ISO AWI 7334, both of which there are kind of respective standards body projects for defining taxonomies for autonomous plant. So thanks very much. Sorry about the little hiccup earlier on, but happy to take questions if there is any.
Do you have any questions from the audience at the auditorium? Otherwise, I had one quick question. Have you noticed any differences, especially when considering autonomous machinery on projects like a national highway versus when you're within a construction site, and how do those show up within the taxonomy?
Yeah, it's really interesting, and it's kind of similar to the comparisons between different industries as well. So for example, in the mining case, you've got huge projects with lots of repetitive processes where kind of automating clearly makes more sense. The reason that we've gone down the granular route with this taxonomy is to give us the fine-grained control to enable the taxonomy to work not just in national highways projects, but within any kind of construction project. So it was very much developed for construction versus national highways specifically, if that makes sense.
Thanks so much, and thank you for the great presentation.
Thanks.
I think